Heating curve. A heating curve is a graph showing the temperature of a substance as it is heated over time. The graph can be used to find the freezing point or the boiling point of a substance. A heating curve has two sections, a flat section and angled sections. Flat sections are where the temperature is not changing, but these are the sections where the substance is undergoing a phase change. Angled sections are where only the temperature is changing. For these sections, the substance is changing temperatures, but not changing phases. The flat and angled sections of the heating curve correspond to our two equations we've been working with, Q equals m times change of h, and Q equals mc change of t. When you're finding the energy for a flat section, you're going to use Q equals m times change of h because you are finding the energy of a phase change. But when you're finding the energy for an angled section, you're going to use the equation Q equals mc change of t because the temperature is changing in that section. This is what a heating curve looks like. The flat point in the lower end of the graph will always be your melting point. The higher flat point is always going to be your boiling point. Therefore, using a heating curve, you can always find the boiling or the melting curve by going to the flat sections and then looking at the temperature in the y-axis. At the melting and boiling points, both adjacent states of matter are present. For example, for the melting point, there is liquid water and solid water present. To find the energy for a heating curve, this comes down to breaking down the curve into its separate parts. The flat part's energy is found by using Q equals m times change of h, and the angled part's energy is found using Q equals mc change of t. A problem will alternate finding energies using this equation. The change in temperature for the Q equals mc change of t equations will only look at one angled part at a time without touching flat sections. The reason the angled parts are not done as one whole equation is that the substance will have a different specific heat based on what state of matter it's in. How much energy does 40.5 grams of water gain if it goes from negative 40 degrees Celsius to 40 degrees Celsius? The specific heat of ice is 2 joules per grams degrees Celsius. For liquid water, it is 4.184 joules per grams degrees Celsius. The change of enthalpy of fusion of water is 333.55 joules per grams. First, we're going to find the energy the ice absorbs to go from negative 40 to 0 degrees Celsius, where it's going to melt. So we're looking at the angled part. So we're going to use Q equals mc change of t. We set up all four variables. Read the question again, identify them, and then plug them into our Q equals mc change of t formula. Multiply the mass times the C times the change in T, and we get 3,240 joules. Now we're going to find the energy needed to melt the ice. This is the flat part, so we're going to use Q equals m times change of h. For this, we only have three variables. We write them down and identify them in the question. The mass is still the same, notice, 40.5 grams. It has not changed between the first formula and the second one. However, this time we are using our change of H of fusion, and it's positive. We're going to find the energy needed to heat the liquid water from 0 degrees to 40 degrees now. We write down the four variables and read the question again. Identify them. Notice the mass still has not changed. The only thing that has changed is the specific heat, 4.184 joules per grams degrees Celsius for liquid water, and the change in temperature, 40 degrees Celsius. and that gives us 6,778.08 joules, and we need 3 significant figures. So we're going to round down to 6,780 joules. Finally, we're going to add the 3 red numbers or energies to get the total energy needed. So taking the first one, 3,240 joules. The second one, which I failed to mention, starts out as 13,508.775, but we're rounding each answer to 3 sig figs, so we're rounding that down to 13,500 joules. So this is our second Q, or energy, and our last one is 6,780 joules, and we're just adding them together. And that gives us a total of 23,520 joules.